Hi, Chem 151 students, and welcome back for our continued lectures here on electrochemistry. So when I finished last time, I was talking about various types of battery chemistry. So batteries are also known as galvanic or voltaic cells, which means that the electrochemical cell proceeds in a direction that is spontaneous with a positive uh, positive cell potential. And we left off. We talked about alkaline batteries. We talked about rechargeable batteries like NiCad, nickel cadmium batteries, and nickel metal hydride batteries. And finally, we talked about lithium and lithium ion batteries, which are the preferred battery technology for lightweight applications like phones, cars, uh, and so forth, laptops, those kinds of things. Um, In this lecture, we're going to continue to talk about, we're going to go ahead and talk about the other types of situations in which electrochemical reactions run spontaneously. Uh, and we're also going to talk about non-spontaneous electrochemical reactions, which are called electrolytic cells. So I finished off last time talking about lithium-ion battery technology, and now I want to talk about a little bit about what's known as the hydrogen-oxygen fuel cell. And so this has been an electrochemical cell that has been proposed for many applications, including including cars. There is a Toyota hydrogen-oxygen fuel cell car that they developed a couple of years ago. And the way that the hydrogen oxygen fuel cell works is that there are two inlets. One is for oxygen, which would come from the air, for example, and one is for hydrogen gas. So one of the biggest challenges of hydrogen oxygen fuel cells in cars, for example, is that you have to have a tank of hydrogen gas, which, if punctured, would be very explosive. And so in the Toyota hydrogen oxygen fuel cell car, they made carbon fiber special tanks for the hydrogen that are resistant to puncture, so that kind of danger would not pose as much of a problem. What happens and the reason why hydrogen fuel cells have not caught on is the difficulty in having good anode and cathode materials. So in the traditional hydrogen oxygen fuel cell, there'll be a porous carbon type of electrodes here, which are made out of graphite. They can conduct electricity, and they have pores to allow small ions and molecules through. The various materials have been proposed for anode and cathode materials, and this is probably the biggest difficulty with hydrogen oxygen fuel cells for practical applications. We want these cathode and anode materials to be electrically conductive, but also to allow the molecules or ions that we want to pass through while others do not. And what happens here is we have oxygen come in one side here, and that will be reduced to oxide ion or hydroxide ion, and then this will attach to hydrogen, which will be oxidized to H plus ions, and together they would make water, which would then proceed out of the outlet here. And you can see the electrolyte in here is hot aqueous potassium hydroxide. So the oxygen here is reduced here to hydroxide. The hydrogen is oxidized to H plus, and then those together make water, which passes out of this this region here. And so the oxidation happens at the anode here, the reduction at the cathode, and the result is a spontaneous electrical charge that is generated. You can also get energy by just burning hydrogen and oxygen, right? We said that hydrogen is explosive, but you can't capture that as electrical energy if you're just burning the hydrogen. So this fuel cell can convert that chemical energy into electrical energy, which can be used to power a car or other device. So that's a hydrogen oxygen fuel cell. Also, another electrochemical process that's that's spontaneous and also very important is the oxidation of various metals, also known as corrosion. Iron in particular, as you're probably well aware, will rust over time in a wet environment. If it's a dry environment, interestingly, the iron will not oxidize, it will not rust in this way, but it will rust much more readily when it is wet. And the reason why is that each tiny droplet on the surface of the iron metal forms a tiny electrochemical cell with a spontaneous reaction that results in the conversion of solid iron to iron 2 ion, and then later further oxidized to iron 3 ion, which then reacts with oxygen to produce iron 3 oxide, which is rust. And so the way this works here is that on the anode region is considered here the region where the metal is, and so in this region the electrons will be lost and they'll pass over here to the edge of the droplet, which serves as the cathode region. So here the electrons travel and reduce the oxygen along with protons to produce water. And the result is that we get iron 3 oxide rust deposited on the surface here. And so the charge here, the electrons transfer directly to through the arrow, or through the metal here. The ions transfer through the solution, and ultimately the iron 3 ions here combine with oxide ions and ultimately form iron 3 hydroxide. And so not only are spontaneous electrochemical reactions used to generate electricity, but also spontaneous electrochemical reactions can result in the corrosion of metals in this fashion. Now, obviously, we don't want all of the metals to corrode. A great example would be your water heater. Your water heater is hot, and so that increases the rate of corrosion, and also it is exposed to water, and it's generally made out of iron. So what will be done to prevent the corrosion of your water heater tank or any other metal that may get holes in it is to put this in electrical contact with another metal that is more readily oxidized, and so is a better reducing agent, you could also say. And so aluminum, chromium, magnesium, titanium, zinc, and other metals will be more likely to become oxidized, and we can determine that based on or at least know that if we have the table here that we've been using, the electrochemical reduction potential table. And so that was here in the textbook in the appendices, Appendix D, which I posted here. And so here again, these are reduction potentials, so this is showing the progress of a metal ion being reduced, and so what we're talking about is the oxidation, or the opposite direction. And so these reactions will be most likely to go in the reverse direction if the E standard is smaller. And so you can see that the reduction potential for aluminum ions to aluminum right down here is negative 1.66, meaning this reaction does not go very spontaneously at all in the forward direction compared to the others above it. It would more likely go in the reverse direction, where the aluminum is oxidized to aluminum 3+. And so the oxidation potential would be the opposite sign of this. It would be positive 1.66. And you know, the higher the potential, the more spontaneous the reaction. So here we can see that reduction potentials for aluminum, magnesium, and some of the other metals that we mentioned here, chromium, zinc, these all have very low reduction potentials here. Zinc, ion, chromium, aluminum, magnesium. And so the opposite directions, the oxidation potentials are quite high. They're higher than iron. So you can see iron is up here. So its oxidation potential, if we reverse this reaction, is positive 0.44. But the oxidation potentials for chromium, zinc, aluminum, magnesium are higher. And so they will be more readily oxidized. So all you have to do to prevent the corrosion of the iron is to put it in electrical contact with a aluminum or magnesium rod, which is generally attached somehow to the outside of the tank, and that rod will be corroded preferentially to the iron. Another strategy is to simply coat the iron with a metal like zinc. So again, zinc is more readily oxidized than iron. And so if you coat the iron with zinc, it will be the zinc that is oxidized as opposed to the iron. And as long as there's somewhere some coating of zinc somewhere on the iron, for example, the iron screw here, it will be the zinc that is oxidized to zinc 2 plus by the same process as iron would be oxidized, as we talked about with the water droplet carrying the ions here, and the interface between the water droplet and the metal serving as the cathode. And so this process of coating iron with zinc is called galvanization. And so if you've heard of galvanized steel pipes, these are iron pipes that are coated with zinc so that the zinc will corrode preferentially to the iron. On your water heater, usually there's some type of a rod because there'll be significant corrosion that occurs over time, and that rod is screwed in and somehow attached to your water heater, so that and occasionally you have to replace that. That's referred to as a sacrificial anode. So here our sacrificial anode is the zinc. And you can see it's because the reduction potential for zinc is smaller, which means the oxidation potential in the reverse direction is larger. And so the zinc is more likely to oxidize than the iron. So this method I said of putting a metal in electrical contact with the iron so that it will be oxidized preferentially to the iron, this is called cathodic protection. And what it means here is that instead of coating the entire metal, we just put it in electrical contact, for example, magnesium, and the magnesium here will be oxidized instead of the iron, since it has a very large positive oxidation potential that you can see here. And then what will be reduced at the cathode, as usual, is the oxygen reduced in producing water here. So attaching a magnesium stake to the iron will corrode the magnesium instead of the iron. It's referred to as a sacrificial anode because over time it will corrode and completely dissolve in the water, and so as ions, and so you will need to replace it from time to time. Finally, we're going to talk about non-spontaneous electrochemical reactions. These are referred to as electrolytic cells or electrolysis reactions. So this is the process of using an electrical current to bring about a chemical change, to make a chemical reaction happen that is non-spontaneous. So there's lots of non-spontaneous chemical reactions that we might want to do. Probably the most common is the purification of metals. So when metals come out of the ground, they are usually not in pure metal form. They're in some type of ore, which is usually the metal in an ionic form attached to oxygen mostly, or sulfur. So you have iron, or you have the metal ions, the positive ions, and the non-metal oxide or sulfide ions or other ions. So when you dig the metal out of the ground, it comes in the form of this ore, and what we'd like to do a lot of the times is take the ore, which will contain the metal ions, and turn those into the solid metals. So you can see for a number of these metals, at least under standard conditions, this is a non-spontaneous process, and so we would have to introduce electrical current in order to cause this reduction of these metals to happen. Of a particular note here is that when we do electrolysis processes, often we do them in aqueous solution. So it's not only the metal that could be reduced, but also it's water itself that could be reduced, which is indicated by this reaction in the orange box here. So if water is reduced, it makes hydrogen gas and hydroxide ion when you balance the equation here. And so the reduction of water will compete with the reduction of other metals. For example, water here would be more readily reduced than aluminum or magnesium. And so if you were trying to reduce aluminum or magnesium in the presence of water, you would have some challenges, because the water, or when they're dissolved in water, the water would want to reduce preferentially compared to the aluminum or the magnesium. If we're at standard conditions, of course, we can alter those conditions so that we can make this more possible. This is the reduction of water. And then also when it comes to the oxidation reactions that are occurring in an electrolytic cell, if they're occurring in aqueous solution, it may be that the water is reduced instead, or the water here is oxidized rather, instead of some other component. So here, if this reaction runs in reverse, this is indicating water being oxidized, losing electrons if this reaction is running in reverse, and it produces oxygen and protons. So the reverse reaction here would indicate the oxidation of water. Now it's important to note that these are E standard values, so these are under standard conditions. These will be different under non-standard conditions, and so generally when we're talking about an electrolysis reaction, it will occur under non-standard conditions, and so I'll have to give you an E for that particular situation. It won't be an E standard, it will be an E non-standard for non-standard conditions, but I would provide that to you for the non-standard E, unless I have you solve for it with the Nernst equation. So let's look at some examples that may make things a little bit more clear. So we can electrolyze just water. So if we put an electrical current through water, at the anode here, we would have water, which would be oxidized here. And when it's oxidized, it loses 4 electrons here, and it makes oxygen and 4 protons. And so that comes straight from this reaction right here. So that's this reaction in reverse, what we've written down right here. And then at the cathode, the water could be reduced here by gaining electrons. And this is this reaction here, but it's been doubled. So the 2 is a 4. It's 4 electrons here, 2 hydrogens and 4 hydroxides. And so that would occur at the cathode. And so here we have water being oxidized and reduced. This is what happens if we weren't run an electrical current through water itself. And so if we add up the results for this reaction here, the 4 electrons here will cancel. So 4 electrons lost, 4 electrons gained. That's why we had to double this second reaction, so we would have the same number of electrons lost or gained. We add 2 waters here to 4 and we get 6. And we got 2 hydrogen gas right here, 1 oxygen gas right here, and then 4 protons and 4 hydroxide ions. Now this is if we put an electrical current through pure water. But what if we have other things in the water? So if we have other things dissolved in the water, it may be that it is not the water that is oxidized. Maybe it is something else that is easier to oxidize than water. Or at the cathode, it may be water. It may not be water that's reduced. It may be something else. It all depends on the relative potentials, which would the relative half cell potentials, which would be more readily happen if you pass an electrical current through the solution. So here is electrolysis of molten sodium chloride. So this is sodium chloride that has been melted. It contains no water. So if you don't have water, you don't have to worry about the oxidation or the reduction of water. You just know that if you've got sodium chloride and you melt it, then what you've got is you've got liquid sodium ions here, and you've got liquid chloride ions. Not aqueous, rather, sorry, liquid. Because they're not aqueous because there's no water. It's just melted sodium chloride. So it would be liquid. So what you've got is you've got these ions floating around. Now when it comes to which is going to be oxidized and which is going to be reduced, this is where you have to use your chemical intuition. I wouldn't say memorize what I'm about to tell you. I'd say try to understand it. So when it comes to oxidizing sodium, you're very unlikely to be able to oxidize sodium because sodium is in group 1 of the periodic table. It has 1 valence electron. So removing that electron is relatively easy to oxidize it, but removing a second electron would be extremely hard because then you have to dig into the core electrons. After you've removed 1 electron from sodium, you've removed by far the easiest electron to remove, the 1 valence electron. To remove a second electron means removing core electrons, which is not easy at all. And then so the take-home message here is if you're trying to decide what may be oxidized and what may be reduced, the cation is more likely to be reduced. It will be at the cathode. When it comes to the anion, the chloride ion, it's negative, one, because it has gained one electron, which gives it a full valence shell with 8 valence electrons. Adding another electron would be energetically prohibitive. So anions are unlikely to be reduced. Just think about it. Anions are negative, so adding another electron to this anion is not going to be easy. They're going to repel each other. So the take-home message here is that the cation is probably what's going to be reduced to a neutral atom, and the anion is what's going to be oxidized, again, to neutral atoms. And so at the anode, we've got the oxidation of chloride ions to chloride gas, and 2 electrons are lost. If we're looking back at our standard reduction potentials here, way up at the top, you'll see the reduction of chlorine gas to adding 2 electrons to make 2 chloride ions. This has a relatively large E standard. The reverse, its oxidation potential is, quite negative actually in standard terms. So what we're looking at here is the reverse of this equation: 2 chloride ions being oxidized, oxidized to chlorine gas by losing 2 electrons. So we're looking at the reverse of this reaction right here. If I move it over, you can see it. So right there. So 2 chloride ions making chlorine gas and 2 electrons. Now, on the cathode side, we have sodium being reduced to 2 sodium atoms. Each one gains 2 electrons. And we've multiplied this whole thing by 2 so that we'll have 2 electrons lost and 2 electrons gained. You always have to have the same amount of electrons lost and gained. So if we look here for sodium, its reduction potential quite small, and so you can see here, if we were to now obviously this is not standard conditions because these are not aqueous, and so the E's for these will be very different than they would be if it were standard conditions. But overall, you can probably tell this is not a spontaneous process. You have to put in a significant amount of electrical current to drive this reaction forward. But if you do, you can take melted sodium chloride and make sodium metal and chlorine gas. And that's a realistic way to make sodium metal and chlorine gas. If, for example, if we see a sample of sodium metal, it was probably made in this way. Or chlorine gas. Chlorine gas is actually more practically made in a different way called the chlor-alkali process, which we will discuss shortly. So if we were to electrolyze molten sodium chloride, so one thing you're going to notice about this electrolytic cell that is different from the galvanic cell is that in this cell we did not need a separation of the 2 sides of the cathode and the anode here. Why is that? It's because we don't need to capture the movement of the electrons here. We are driving the movement of the electrons. And so it's okay that we do this all in one vat of melted sodium chloride. So there's the sodium ions liquid and the chloride ions liquid here. We have some type of power source like a battery. And again, the anode is going to be where the oxidation happens. Anode, remember, anox red cat. Anode is oxidation, so you can see the 2 chloride ions losing 2 electrons and making chlorine gas. That is the oxidation happening at the anode. At the cathode here, the reduction is happening. 2 sodium ions are being reduced to sodium atoms. And so what you'll see here when you drive this reaction is you'll see chlorine gas bubbling up off of this anode here, and you'll see sodium metal, liquid sodium metal depositing here on this cathode here, and probably dripping to the bottom or floating to the top here, depending on its density relative to the molten sodium chloride. It would drop to the bottom. It would be more dense, I think, than molten sodium chloride. The difference, so one important difference between the notation here used for electrolytic cells and for galvanic cells is in electrolytic cells, the anode is called positive and the cathode is called negative in terms of sign. And so that's the big difference in the notation between galvanic and electrolytic cells. Why is it this way? Well, it's because we're having to pull the electrons here away from the anode. We have to pull them away. We have to put in energy to make this happen. And so that is indicating that these electrons are essentially attracted to this anode, and we have to pull them away from the anode. So it makes sense to label the anode as positive in a electrolytic cell, whereas in a galvanic cell we would label it negative because the electrons very freely move away from that electrode and they're repelled by it. But here they're attracted by the anode and we got to pull them away from the anode. So we call the anode positive. And then for the cathode is called negative here because, again, if this cathode is negative, this means the electrons are repelled by this cathode. However, we're driving these electrons to the cathode using an external energy source, a battery, for example. And so that is the big difference between notation for galvanic cells or voltaic cells, as we studied earlier, the spontaneous ones, versus the non-spontaneous electrolytic cells. Anode is still oxidation, cathode is still reduction, anox red cat still applies. The difference is the anode is positive for electrolytic cells and negative for galvanic or voltaic cells. And the cathode is negative for electrolytic cells and positive for galvanic or voltaic cells. Okay. Now, so that's the electrolysis of molten sodium chloride with pure sodium chloride. Now we're going to start, oh yeah, before we continue, this is a way in which you could conduct electrolysis on molten sodium chloride, but practically speaking, it's not very handy if you're trying to get the sodium metal in the chlorine gas, because the chlorine gas will just bubble up and go out into the atmosphere and it'll be hard to catch it. And here the sodium will just sink to the bottom, and again, it will be hard to get it. It will just be on the bottom here. So from an engineering perspective, the way in which electrolysis of molten sodium chloride is generally performed is in this device, which is called a down cell. And actually, I was incorrect in my assumption here. The sodium is floating, so we can see it here floating. Whoopsie, sorry about that. But the result here is that the anode here is this graphite material, which is in the middle, and all of this is the molten sodium chloride. So the positive terminal of the battery is connected here, or the power source, and the result is that the chloride ions are oxidized to chlorine gas, and that chlorine gas bubbles up right through the middle and can then be easily captured for use later, and you get pure chlorine gas. For the sodium, the actual casing of the steel cylinder itself is the cathode material, and so the electrons travel through this casing into this area here, and then sodium is then reduced from sodium ions to sodium liquid, and that liquid then floats here and passes out of this tube and can later be collected, and the sodium chloride can always be refilled in the top here. And so that's practically speaking the way that the electrolysis of molten sodium chloride occurs. Now, there are other electrolysis processes. Perhaps the most important electrolytic process is the electrolysis of aqueous sodium chloride. This is also referred to as the chlor-alkali process. It is perhaps the most important industrial chemical reaction, or one of the most important. So in order to make this happen, though, we're going to have to expose it to what's referred to as an overvoltage. So you guys know that, for example, if E is 0, or delta G is 0, that is indicating a reaction that is at equilibrium. It's not spontaneous. So if we provide enough voltage to get the E to 0, or essentially to be equal to the negative cell potential of the electrolytic cell, that will not be sufficient to drive the reaction forward. We need a over voltage, so we need a voltage that is beyond what will bring the total E of the cell to 0. We need it to be positive, so this reaction will be driven forward. This is referred to as an overvoltage. Also, when we're talking about aqueous, the electrolysis of aqueous sodium chloride, here sodium chloride is a neutral salt, so the concentration of H plus and hydroxide will be 1 × 10⁻⁷, not 1 molar. So we're going to have to use a non-standard E. And again, I would provide this to you in a problem. So at the anode, there's two possible reactions that can occur. They're both going to be oxidation reactions. But as we discussed, in molten sodium chloride, the oxidation of chloride ions will occur at the anode. However, we do not have molten sodium chloride here. We have sodium chloride dissolved in water. So assuming we have 1 molarity, though, of chloride ions, we can use the E standard for this. And this is obtained directly from the table here. We can see that the E standard for the reduction of chlorine is positive 1.36 here. Let's see, and so whoops. Anyway, so the E standard here being for water here is going, so the E standard for the chloride is going to be greater than the E for water at its non-standard conditions with a 1.4 volt overvoltage. And so the chloride ions will be oxidized more spontaneously than the water. So it will be the chloride reaction here that occurs at the anode. Now at the cathode, there are two possible reactions. Again, here we can have the reduction of sodium as we did with the cathode, or as we did with the molten sodium chloride. That has an E standard of negative 2.71 volts, very non-spontaneous here under standard conditions. Under the non-standard conditions for water, its reduction here would have an E standard of negative 0.42 volts with a negative 1 volt overvoltage. And so here it would be the water reduction here that would be more spontaneous because the E is larger. So the E is larger for the reduction of chloride than it is for the reduction of water. So in aqueous sodium chloride, the chloride will be oxidized here, and it will be the water that is reduced because its potential here is much larger than the E standard for the sodium. And so that's how we choose which reactions will occur based on the E values. Whichever one is larger will occur at that place. Remember, anions like chloride will be oxidized, so that's the one that may occur at the anode along with the oxidation of water. What may occur at the cathode is the reduction of the positive ion, like sodium here, or the reduction of water. And we have to choose which one is more likely to occur. It will be the one with the higher E here, more spontaneous. So overall, the electrolysis of aqueous sodium chloride will have the oxidation of chloride at the anode with it, and we'll have the reduction of water at the cathode. So we'll write this reaction at the cathode. So overall, our electrons here cancel, and we can add this up to an overall reaction. So the overall reaction will have 2 waters and 2 chlorides on the left. So 2 waters, 2 chlorides, and it will have chlorine gas and H2 and 2 hydroxides. And so what makes this an absolutely amazing reaction is that doing one electrolysis process of the electrolysis of aqueous sodium chloride gives us 3 extremely useful industrial products, which include pure chlorine gas, pure hydrogen gas, and hydroxide ions, specifically sodium hydroxide, because the sodium ions will still be in there. So we get chlorine gas, hydrogen gas, and sodium hydroxide all from one process. And the sodium hydroxide you have used in labs is probably obtained by this process. We simply take salt water and apply electrical current to get these pure products out. Extremely useful reaction that we depend on as an industrial society all the time. Now here is the practical cell in which this reaction is done. And so you can see that saturated sodium chloride is introduced into the left side of this cell here. And this is the anode side. So this is where the chloride ions will be oxidized to chlorine gas. And so you can see there's a region above here where the chlorine gas can come out and be collected as the chloride ions are oxidized to chlorine gas. While this is happening, the sodium ions migrate through a semi-permeable membrane, which is placed between the anode and the cathode sides here. And then on the cathode side, we have the reduction of water. And so this produces hydrogen gas, which is collected at the top, and then 2 hydroxide ions, which then combine with the sodium make sodium hydroxide. So here is where we get out the chlorine gas product at the anode. Here's where we get the hydrogen gas product at the cathode, and also the sodium hydroxide product. And in this one beautiful industrial process, we can get 3 very, very useful chemical products. As I said, electrochemistry is very commonly used to purify metals as well. For example, around 10% of all of the electricity used in the United States is used to produce aluminum metal from aluminum ore. So what we do is we take aluminum ore, which is aluminum oxide mixed with some other things, and then heat it up very hot in order to melt it. And then once it's melted, we pass a high voltage electrical current through it through graphite electrodes, which they will not react in this process. They are unreactive electrodes, but they do conduct electricity. And so what will happen is that electrons will be provided here to aluminum ions, which are aluminum 3+. This will reduce them to aluminum metal. That aluminum metal is more dense than the molten aluminum oxide, so it will sink to the bottom of the tank and be collected out of a spout at the bottom of the tank. And this continuously goes and goes all the time. And we'll have a problem at the end here where we talk about how much aluminum can be produced from a certain amount of electrical current. Also produced, purified by electrochemical processes is copper. So any of the copper used in your phones or electrical wires in your house, any of that is produced from copper ore. And so we'll have here copper in solution here, or we'll have copper ions and others that come in solution from an impure copper anode. And so we attach the positive terminal or the power source to an impure copper anode, and then also immersed in solution here is a pure copper cathode. And so these slabs here you see, these are these electrodes. They're alternating impure copper, pure copper. And what happens is that the impure copper and other metals are oxidized at the anode terminals, which are connected to the impure copper here. And then the copper ions are preferentially reduced here at the copper cathode, which will produce, which will have the copper deposit on this pure copper cathode, making an even larger pure copper cathode. If you look at the reduction potentials for zinc and iron, you'll see that they're lower than for copper. We can go back here and look. So for copper, its reduction potential is positive, or its standard reduction potential is positive 0.34 volts. For zinc and for iron and other impurities here, their reduction potentials are much lower. And so the copper will be preferentially reduced here at the cathode, and so you'll have purified copper depositing at the cathode here. Okay. So how would we determine how much purified metal or electrolysis product we could get by running a certain amount of electrical current for a certain amount of time? In a problem like this, you'll be given the amount of current that is run through the electrochemical cell and how long it is run through. You'll use that to determine the charge that was passed through the electrochemical cell. Remember, current is in amps, amps are, just a reminder, amps are coulombs per second. And so if we have amps or coulombs per second multiplied by time, the seconds will cancel and we'll get the charge in coulombs. After that, we use Faraday's constant, which tells us how many coulombs is the electrical charge of 1 mole of electrons. That allows us to convert the charge to how many moles of electrons were transferred. We can then use the stoichiometry of the reduction to determine how many moles of the product are produced per mole of electron that is provided. And finally, we can convert those moles to grams of product. So an example problem like this is and this is a realistic problem for aluminum refining factory. It will draw 2 times 10 to the 6, let's say, or 2 million amps of current for 4 hours while running the electrolytic cells in their factory to produce aluminum from aluminum oxide. Assuming 100% efficiency, how many kilograms of aluminum are produced? And so the aluminum oxide is composed of aluminum ions, which are +3, and oxide ions, which are -2. What we care about is the aluminum, because we're trying to produce pure aluminum. In order to produce pure aluminum, we would have to add 3 electrons to get solid aluminum. And so our relationship here is that we're going to need 3 moles of electrons to produce 1 mole of solid aluminum. So we're going to start here with the time that we are running, 4 hours. But remember, amps here are coulombs per second. Coulombs per second. And so we're going to have to convert those hours to seconds before we can use the amps to determine the coulombs of charge that were transferred. So we're going to start with 4 hours. We're going to convert that to minutes. 1 hour we'll put on the bottom here so that hours cancel like that. And that is equal to 60 minutes. And then we want to convert minutes to seconds. So we have 60 minutes, or sorry, 1 minute here. So minutes will cancel. And that is equal to 60 seconds. And so that will get us our number of seconds that this electrochemical cell has run at in this factory. So we'll have 4 times 60 times 60, which equals 14,400 seconds. Okay, so now we're ready to convert seconds to the amount of coulombs of charge transferred in that time using the amps, or the current. So 14,400 seconds was how long we had 2 million amps of current running. So that means per second, that is 2 times 10 to the 6 coulombs, or 2 million coulombs. We had 14,400 seconds. This ran. Every second was 2 million coulombs. And so that gives us our number of coulombs of charge. But we want to convert that to a moles of electrons that is equivalent to that charge so that we can do our stoichiometry here. So we're going to use Faraday's constant. So it is that for coulombs, it is 96,500 coulombs. And that is the charge of, coulombs cancel here, that is the charge of 1 mole of electrons. So now we have the moles of electrons. Now we just need to convert that to how many moles of aluminum could be produced here. So it is 3 moles of electrons, which is what I'll put on the bottom, so moles of electrons cancel, make 1 mole of aluminum. We get 1 mole of aluminum right there. Okay, so now we can multiply that. 14,400 times 2 10 to the 6, divide by 96,500, and then divide by 3. And we get about, to 3 sig figs, 99,500 moles of aluminum. 99,500 moles of aluminum. Now all we got to do is convert those moles of aluminum to grams. So if we look at the periodic table, you may want to look at yours right now. 1 mole of aluminum will weigh about 27 grams. And so 99,500 times 27. Now, in the end, I asked you how many kilograms, though. So this is how many grams. So we want to convert grams to kilograms. And so we put 1,000 grams on the bottom. That is equal to 1 kilogram. So grams of aluminum cancel here. So now we divide by 1,000 to get the kilograms. And that gives us, to 3 sig figs, 2690 kilograms. 2690 kilograms of aluminum. And that is the way that you solve one of these electrolysis problems for how much of a product could be produced based on running a certain current in amps for a certain period of time. And that is the last type of problem that we'll do. So in this lecture, we covered corrosion, which are spontaneous electrochemical processes that occur resulting in the conversion of metals to metal oxides, or in particular iron to rust. We discussed a variety of different electrolytic cells, including electrolytic cells and electrolysis of water itself, pure water, electrolysis of melted ionic compounds, sodium chloride, and also the electrolysis of aqueous ionic compounds, in which you must choose what will be oxidized and what will be reduced, either water or in the case of the anion, that may be oxidized, or the case of the cation, that may be reduced. And those are both competing with the oxidation and reduction of water. And then finally, we did a problem here where given a certain amount of time, a certain current running, how much product could be produced from an electrolytic reaction. And that concludes all of the electrochemistry chapter and also all of the Chem 151 material. So for the remainder of the week, I would encourage you to review the material that we've discussed before and begin to get ready for the final. Of course, focus on the electrolysis material. There will be a quiz at the end of the week, and then finally you'll have the final exam, which will include the ACS exam with questions from all of general chemistry, and I've provided for you an ACS exam study book that you can use to kind of get an idea of what those questions will look like and practice a little bit before next week. And also the general exam here, which will focus mainly on the thermodynamics and electrochemical things that we have learned, but there will be a little bit of questions on other topics as well. Of course, it's cumulative, so I'll pick a few questions about some of the most important topics and ask those as well. And then finally, there will be the lab final, and that lab final will be a take-home lab assignment, which you will complete. It will be just like another lab, but it will include aspects of many of the different labs we've done over the course of the semester. So I wish you good luck in your studying. Make sure to come see me at office hours both this week and next week if you need help. Next week, of course, there will be no new material. It will just be the final exam. So have a good one, and I will see you guys later on. Bye-bye.